So here to talk about a relatively significant project we've gone through at LINX on our LON2 network, where we deployed, as hinted by the title, an open networking disaggregated solution. So a little bit of a background on the project. We actually run two networks in London as part of the London Internet Exchange. We have the one we call LON2, which is a router-based, traditional Cisco, Nokia, Juniper style solution running VPLS, and LON2, which at the time was using layer 2 technology, not quite spanning tree ring protection, but that generation of technology using a traditional layer 2 vendor. We actually had attempted to move LON2 to VPLS, but hadn't quite succeeded. Then going back to 2015, there seemed to have been a tipping point where the bulk of the orders stopped being at 10 gigs and appeared at 100 gigs, and we could see that we needed to do a change, in particular on LON2, with that extra uptick, and also the core was going to need to adapt to it as well. Even if we didn't change vendor, something needed to be done. So we didn't just do a vendor selection. We didn't want to do a like-for-like replacement. We started talking strategy options. What can we do? And that was very much the steer I got from senior management. Take it as an open book. And we've looked all the way from a second traditional router vendor to something that's what was at that time the new innovative idea of doing open networking and disaggregated. And as you can guess from the subject of the presentation, it was a second. Actually, an interesting bit of history. It was actually in San Francisco at a NANOG. We often combine NANOGs with talking to our local US vendors, as the existing LON2 vendor communicated that as it stood with their strategy, there wasn't an overlap. So we actually knew at that stage that we were with a new vendor. So we looked for the best strategy. It wasn't, okay, that one's still working. It wasn't just a traditional select something off the shelf, except for the layer 3 vendors. There's a number of requirements that IXPs have that don't just work. I'll cover more detail on that. But having taken all the strategies, what we actually then did, because membership led, is go to all our members. Those in Europe and London we visited then, but then at 66 down in San Diego, we took the opportunity of quite a few of our members actually being in the same building to actually talk to them direct. So I said we had a couple of things that are different. Now the first one, if you're a carrier, you know that, the port is a demarcation. If you're running a hyperscale data center and you have some unexpected traffic, you call your server guy and say, what on earth are you doing? And you figure it out together. As a service provider, not an option. So you need a lot more instrumentation at the demarc than if you can just peek the other side. The other thing is best practice is you don't create a giant layer 2 broadcast domain and connect a whole range of speeds and just connect any port anywhere. But at IXP, that's what you sell. You have no choice but to offer that. It also means that flooding that can be just accidental and tiny for a member with multiple 100 gigs, a member with 1 gig really does not appreciate, and it can trigger something that's effectively an outage. So the other challenge we come up is max security. Now, if you've ever dealt with a third-party data center and you report a fault on the circuit, chances are they'll put a loopback. And if you've ever operated a layer 2 network, loopbacks are a really bad thing. So all IXPs a long way back implemented max security so only known MAC addresses are allowed on ports. The challenge, in addition, with Broadcom is the way they've implemented learning. It's a fixed pipeline, it does certain operations in a certain order, and learning occurs before the MAC ACL. So even with the MAC ACL, resources will be consumed by the learning, packet uplifted, and all of a sudden your forwarding capability will be reduced, even though you're going to drop it and ignore it. So with the Broadcom, we know that has to actually be switched off. Finally, like a lot of exchanges, we have partner ports. We are actually in 12 buildings in London, but that's nothing compared to the whole city. So for potential members that can't just order a cross-connect to reach us, we use partners for the last mile. They have a port, or maybe a lag, and present each individual member to us on a VLAN. And we have to do MAC security, not on a port, but now on a VLAN. We need to do some form of shaping and policing to make sure that the right bandwidth comes in on the VLAN. But the thing that really does the head-in of any traditional layer 2 vendor is that you now have, for example, VLAN 7, 21, 415, and 1052 being mapped to VLAN 100. And having multiple VLANs being mapped to a common VLAN, yes, if you're a layer 3 vendor, it's a port unit, it's a sub-interface, but if you're a layer 2 vendor, that really does your head in. So the early steps of the project, how did we get here? We hadn't at this stage decided we were going disaggregated, but the best person we found to work in the disaggregated space, or the first one, was Edgecore Network as a hardware provider. They're part of the Acton group. They're quite large ODM, OEM manufacturer. The chances are a good proportion of the people in this room have deployed their equipment, maybe not aware of it because it had someone else's label on the tin, but pretty well respected. We did a POC with them, and it was a failure. In particular, the exchange features were fragile, was a polite word I settled on. We called the POC off early. There was no way it was going to pass. But very luckily, Cathay Pacific did not have availability on the very next flight. So we could have gone sightseeing, but instead we actually talked to them and analyzed why it failed and figured out really what was required from a NOS. And they went around, they didn't want to give up on the business, and actually, through their relationships in the open networking, found and introduced us to IP Infusion. Little background on them, those who have seen this presentation about Zebra, actually, IP Infusion are founded by the original Zebra coders. But as a strategy, having moved away from specialist stack vendors against someone else's label, they're trying to sell directly NOSes. They worked with Edgecore, provided a demo, actually in particular focused again on the exchange features and went, I think we know what we're doing. It was an I think, but that at least got our interest. But the other bit was the commitment. And one advice I'll give to anyone on the start of a difficult project is make sure that there is a commitment on the other side. And relationship 101, if things are tough when things are going well, you're doomed when they go hard. So actually believing that we could form a partnership was key at that scale. So our conclusion then is, if this works, it's the right choice. We agreed a target solution, EVPN. I think at this stage of Nanog, most people should be reasonably familiar, but the important bit is that instead of data plane learning, which has a whole load of bugs associated with it or behaviors you really don't like, this is all programmed. As soon as a MAC address is known in one location, it's propagated by BGP. And at that point, you know that if it's not known on one individual router, it's not known anywhere. So the same way as if you don't have a matching prefix and no default route at layer 3 you can drop, you can do the same thing, and instead of having the default behavior of flooding unknown traffic, you can change your default behavior of dropping unknown traffic. Other advantage, because it's a layer 3 overlay, it's tunneled, so you don't need to do a MAC flush reconvergence, so significant savings there. Also had other features that we're looking at. Keybit, discussed with the vendors, agreed the technical solution. The key bit that we had, in addition to EVPN, is we really want to reduce background traffic, so wanted to have proxy op and proxy ND. Proxy op, for those who are less familiar with that bit of EVPN, is you can program through BGP not just the the MAC reachability, but also the MAC to IP, the ARP resolution or the neighbor discovery resolution. And that gets flooded, and that means that whenever there's an ARP, instead of it being flooded to 500 or so members, that one ingress router knows the answer and give a proxy response. But as always at the beginning of a project, option to fail back, because the last thing we wanted is halfway through the migration, in comes a bug. It somehow would surprise one vendor. So all of these features we came in had the option on a particular member, if there was an interop, to selectively switch it off. Fortunately, we didn't have to, but that was the approach that we took. And the other thing is we wanted to reduce as much background illegal, as much as we spend a lot of time telling our members, switch everything off, don't send us DEC mop. For anyone that's used Cisco, that's one that usually doesn't get switched off. It's far better if the Exchange fabric just drops it. Now, if someone really is sending bad traffic, we move them into quarantine. It's kind of the naughty step. You go in, and then we'd actually want to see everything. But in the Exchange, we want the ability to lock down to as much as possible known good traffic. So agreed features, agreed target. And I've just pressed back. I was wondering where that was very familiar. One question I often get asked is, why did you not go for more SDN central controller? And being perfectly honest, it's the wrong DNA for LINX. We started as a team of network engineers. I mean, we all could code, but we were primarily network engineers. And our software team would primarily designing things for internal use, nothing mission critical, and they weren't set up for mission critical. We were building a software team, and in particular focusing on automation. But if we throw at that team, and now you need to build and maintain a mission critical SDN controller, that would have probably overstretched the team. And the extra thing is, if you want fast convergence, if it's controller-based, you then really need it to converge in the data plane. The management plane is really quite slow convergence. So as we couldn't do data plane convergence, we needed to do the control plane. So here we are, back in February, started the real work. We now decided who we wanted to. Which brought us to July. But as you can see, quite a gap before we reach live, which was in June. And being honest, a bigger gap than we thought it was going to be. Couple of surprises. Bringing this one is probably the biggest shock. Initially, because they had a VPLS code and we were just going to add the EVPN control plane, we thought, okay, EVPN over MPLS. A challenge in particular with the Broadcom ASIC is there's a limit of how many labels you can remove in one go. An entropy label, which is 2 labels, was a non-starter. Even the ESI label for multi-homing was 1 over budget. We actually found a way to get around that, but that wasn't as to the letter of the RFC, so we would have had some very interesting interrops if we went down that path. Another thing that was suggested, you can go through the pipeline twice, but you're basically leaving half your bandwidth behind at that stage. Other thing we're getting from Broadcom is the actual MPLS layer 2 was designed for VPLS. Subtle difference, but on VPLS, pseudo wires are bidirectional, so you have 1 label for each remote PE. On EVPN, it's a common label, so all your remote PEs use the same label. So when you get and decapsulate a frame, you don't know which PE it comes from. You don't need to do data plane learning, so it's no longer a requirement, and it makes the protocol simpler. But if all the testing was based on 1 implementation, they were getting nervous. And finally, each LSP consumes an interface in the interface table. And because of our scaling forecast, we realized that n squared was going to kill us far sooner than we wanted. Broadcom, absolutely not a go at them. They were very supportive, but in the end, we went for VXLAN. It already existed. We'd already been working a lot on EVPN, so it was really taking a lot of the parallel bits of codes we've been working on and mixing it together. We had a few limitations, a lot around convergence, but we thought we could work around them. Going a key bit on the convergence that we found is that it was quite dependent on topology, because the challenge you have, your control plane can be very fast and knows exactly what needs to be done, but you then need to go and program the underlying ASIC, and that can actually take a non-negligible amount of time. And the worst is if you need to reprogram the actual VXLAN tunnel. So if the reconvergence at ingress was seeing 300 to 600 milliseconds, whereas if it's not at the first hop, it was half of that. And to illustrate how you can get around that, taking an east and a west dark fiber and 1 member-facing switch, if you have a cut on the dark fiber, the reconvergence occurs on the member-facing switch that basically says, oh, well, don't send it via switch 2, send it via switch 1. Next hop for the VXLAN channel changes, it needs reprogramming. If there's any local replication that needs changing, that's actually quite a slow push to the ASIC. If you put a spine in between, and this has advantage on scaling anyway, but if you put a spine in between, you go through the very same scenario, fiber cut is now the spine switch, which reconverges. Next hop for VXLAN, unchanged. It's a spine switch that does the reprogramming, no VXLAN tax. Question would be, okay, well, you have that reconvergence if you lose a spine switch. But now it's ECMP. We were sending previously to 2 spine switches. One goes down, it's deleting an ECMP path as opposed to reprogramming the tunnel. And that actually is 50 to 100 milliseconds reconverging. And if there's an ECMP flip that's not on the tunnel endpoint, that's about 50 milliseconds. And just for extra data, losing a link and a lag well below 50 milliseconds. One tax we do have compared to MPLS, MPLS you can have standby pass and then preemption in a hold time before it reverts. IP routing, as you probably know, reroutes immediately. So you can get a hit if you need to reprogram a tunnel on restoration, but that is below 50 milliseconds. But in case of churn in particular, we did want to put mechanisms for flat churning. If not, we'd get extended drops. But the key bit is it was better, and I really should have said much better than the previous convergence. It wasn't quite as good as MPLS, but it was close, generally not picked up by our members, and whereas the previous ones, there are a number of failures that were visible. So a few details on the technical solution. So leaf and spine, I think that's relatively well known, and that helped with the convergence. We went for EVPN and proxy ARP. That was really easy for IPv4 because we only allocated one IP address, so it was actually in our CRM where all the MACs were and where all the IPv4s were. For IPv6, we actually allocate a range based on AS numbers, and we hadn't policed it, so we actually didn't know which address within the range was deployed and where. We have a data cleanse to do before we can switch on IPv6. So those on the exchange, if we start asking about IPv6, that's because we want to switch on proxy ND. But proxy ARP, even though we have the ability to selectively switch it off, we fortunately haven't had to. Another interesting thing that we picked up while testing as an extra feature is MAC hold down. It's actually not that well expected behavior that you get on a layer 2 network. And the behavior that you have on the FTB is that a MAC on the egress switch will have an entry saying that MAC address will be on interface 23. And if interface 23 goes down, it's no longer valid entry and it gets deleted. And with the VPN, it'll actually work quite fast. It'll go and send a BGP update, much better than pre-EVPN days where it's timeout, but there's still a delay as BGP converges. At that time, you actually get pretty bad flooding because rate limiting of unload traffic is done at ingress. So the egress switch deleted its route. The ingress switch that should be throttling that traffic doesn't know that it's not deliverable, so we'll deliver it absolutely full speed to the correct egress switch, which will then flood it to all the ports. Graph, this was something we actually picked up during the migration. We had actually a quality of service probe that we hadn't migrated until the end of the migration. So you can see a number of the big members. These are 5-minute averages on a gigi port. If you looked at the instantaneous, now we don't have the graphing system for that, but if you look at the instantaneous data, it spent a while at 100% each time there was a port that went down. So that was the old layer 2 behavior, and actually you still have that without the MAC hold down on VPLS, but EVPN plus MAC hold down, that replacement graph basically just removed the blue and it's just no flood. And then we went beyond. We run micro BFD so that if we lose a link in the lag, that gets detected 4 milliseconds. We spent a fair bit of time finding out how fast to tune our SPF. We wanted it to be as fast as possible, but not too fast. A fair bit of, talked about the topology optimization, and the link dampenings have been added. An important bit about the whole project, and this is explaining a bit of kind of what member base means, kind of an easy word, is we couldn't deploy something and say, well, this is really for lots of capacity for our big members, or this is just for small members. So we had to be able to communicate why it benefited everyone. And best is to pick at least the outliers. A challenge we had, in particular with 100 gig orders, is the previous ports were expensive, sometimes required chassis upgrades. If there was an unforecast order, we were nowhere near our target turnaround delivery time. Whereas new hardware, A, there's a lot more capacity and a lot more inventory, but B, we actually can have inventory sitting with pre-built designs, which means that at worst, it's one maintenance window. So within a fortnight, the capacity will be there, but typically far faster than that. So much faster provision time for big members. The small members is all that thing about getting rid of the broadcast traffic, getting rid of background traffic. So if you have a 1 gig port, the chances of you having a significant amount or even all of your capacity being hit by traffic that you really don't want is being reduced. And of course, something that is a benefit for everyone is quite a bit of a lower cost. And throughout the project, we have been and still are passing those savings on to customers as it's not the competitive pressure, but it's still the pressure of a member-based organization. The last bit to go through is a kind of summary of the project steps, what happened in those 2 years. I'm going to go relatively fast through here, but there was quite a long time of prototyping. That was when we were learning, fine-tuning the designs. They'd throw us something, we'd give feedback on usability and send it back. That took us up to November. In November, we had something that, if it was bug-free, was deployable. And then we had a hardening phase where we stopped adding features. One of the reasons that was quite an extensive process is whenever we picked up a bug, we did a testing failure analysis and increased the coverage of the testing. And because that was a lot of test cases added very late, they weren't automated, or before they could do the test run, they actually had to write the testing automation, so it took a little longer. We found a few, mainly through an approach that was slightly mischievous. As opposed to the testing that IP Infusion did, which is automated, a lot of the tests that we were performing as users, we trained the engineer and gave them rough instructions of do X, but didn't tell the engineer how to do it. And you ask 5 engineers to do the same thing, and somehow they managed to do it in 7 different ways. So we found a few bugs that way. But that's the good news. We then migrated over just over a month. We did 1 pilot site, waited for any surprises. We actually did pick 1 traffic type that was left programmed on the ASIC that we hadn't tested, hadn't thought about. It was a packet that looked like RIP but wasn't really RIP. Caused 2 short network events, but the good thing is all the hooks we did for instrumentation and testing were there to address that. And that broken rule can be reprogrammed on the ASIC as opposed to requiring a software upgrade. The old LON2 equipment definitely did not want to go without a fight. It gave us far more grief than the equipment that replaced it. So we're now live. Being brutally honest, it actually went better than hoped. I was quite nervous end of last year, beginning of this year, and I'm really glad that so far no issues. We have done 1 software upgrade for last snags, the temporary fix, to make those permanent, but basically it's now live. Any questions? Assuming I got a little bit of time.
Andrei Khomyakov, Athena Health. Did you end up using any automation? And if you did, what is it? What tool are you using for automation?
We haven't switched it on yet, just to gain resources internally, but it will be netcomp. We were initially going to look at Napalm, but instead we've gone for I was going to say PyCharm. It's on GitHub, and I've really got a memory blank of the name of the project, but it's PyOknos is basically something we have, it's on GitHub that basically for Oknos pushes the configs and it's based on Ginger templates.
Thank you.
But it's basically netconf.
Thank you very much.